Today I'm going to present a paper on designing human-robot collaboration as a joint cognitive system. My name is Angelina Kozhevnikova, and here in the room there is also my co-author, Daniel Hall. A disclaimer before I start the presentation. Presentation acts as a teaser and does not replace reading the paper. So for any details, please consult the paper. And to start the actual presentation, I want to give a bit of context. It was developed during a long project, 10-year project called NCCR, around digital fabrication and architecture. And thank you. Yes, so okay, I hope I have my audience now, thanks. The research started in the end of this project once a lot of technologies were developed, but then the adoption problem remained central and remained a big concern. So there was a need for more system-level thinking and approach. And to start, we first looked back into definition, what human-robot collaboration actually means outside of what I call, sci-fi and a lot of unhelpful cultural understanding that we all have. So, and we defined it as essentially humans working jointly with robots or together in a specific construction task, and each role must be capable of making contributions to the overall system, right? So the machine controlled by a computer. Machine could be anything, computer could have any kind of system. All right. And why we went back to the definition, because as soon as we started to look into the state of research on human-robot collaboration construction, we quickly saw that common definitions come from manufacturing and warehousing. So the paper that is literally used to back up most of the claims is specifically focused on industrial settings. And if someone ever worked in those industries, there are like quite specific ways it's created, and there are repeated production cycles, standardized materials processes, predictable, heavily controlled environments. That's very important for robotics. And versus construction industry is actually quite opposite in many ways. It's unstructured, there is high variability in tasks and materials. Sometimes uncertainty comes from materials itself. So there are multiple uncertainties on different levels. And there is a big reliance on situational judgment and embodied skill, also from a system level perspective, the way construction is organized itself as an industry. So, and it was also interesting to see that actually research started almost a half century ago, but the adoption of robotics is very limited, to say the least. And we started to think maybe we could look into alternative models on how to approach this clearly difficult topic. We found a very interesting, useful community called Joint Cognitive Systems that were heavily involved into in aviation, healthcare, and nuclear sectors. So, which are industries with relatively high human-robot systems adoption and similarly safety critical. And where, there is a lot of reliance on human judgment, dynamic, uncertain situations. And the main idea here, and also of joint cognitive systems, is that it's a distributed cognition, which means we approach robotics as part of a joint cognitive systems with people. So it's distributed across people and tools or machines and so on, right? Therefore, we need shared situational awareness, and the question is of coordination. And here is pretty much the difference between looking into more classical human-robot interaction view, where the focus becomes quickly the focus on designing an interface between two separate components, versus the view of the community that we studied called joint cognitive systems, where essentially physical separatedness does not mean functional separatedness, and the focus becomes on designing a joint, a team effort. And maybe a little bit about the overall principle, you could even call it philosophy, that guides the decision-making when designing robotic systems. Usually, a lot of purely technical approaches are based on substitution myth, which is the belief that machines can take over human tasks without broader consequences for the system. And they usually come as two principles. One is leftover, so usually automation comes first, and then humans are left with either, with work that cannot be automated. Rather, it usually is rare, irregular, so something that designers cannot even predict themselves, or very trivial that is too expensive to automate. And the problem of this approach is that users tend to develop workarounds that compromise their safety. So, since it's developed without users in mind. Then we have compensatory principle, where essentially is a static approach where we compare who is better at what, and without any kind of time-based component, and how people evolve their skill set over time and in interaction with robotic systems. So usually it tends to confine workers to supervisory or advisory roles with limited control, and it leads to alienation and difficulty to justify the value of their own work. And there is a new approach developed in the 90s, where essentially the question becomes, how can human and machine capabilities co-evolve under changing conditions? So the change is primal and is a very time-based approach, essentially, and very sociotechnical. That means that we need to look at all components together, not in separation. And here we go to our research design. So essentially, we looked into a lot of studies on human-robot collaboration and construction to understand how it's studied. And the results were, it's very fragmented and technology-centric. There are only experimental studies, sometimes demos. There is no attention to adoption, and human role is vaguely defined as human without any specification who is this human. Then we use joint cognitive systems as our theoretical framework, and which provides systems perspective, developing safety critical domains, and with established real world use. And to complement this theoretical framework, we studied also meaningful work studies that provided organizational perspective, psychological, and what's important is post-adoption work experience, right? So studying actual workplaces where automation was introduced and how workers adapted to that change. And here are the main components of the framework. We are still working on it, so it's very much work in progress. But essentially, it's organized through three different, what's important, interconnected lenses. They are more purpose-driven, design-led components rather than separating into different groups that don't connect to each other. And essentially, they focus on work part, which is task and agent design, task structuring, resources, but also from both sides, from automata, from robotics, but also from human HR. And then coordination and communication, which is the primal problem in this framework, and also in many ways linking, right, the design of robotic systems itself and worker well-being. And here it's important to state is well-being, because if you define the goal as for example, just safety, then the problem becomes a problem of collision, as we just saw, which is a good problem to solve, but is that the goal that we want? And I'm going to quickly go through some parts of it. Essentially, for example, part of task and agent design is time-based collaboration design. And here we look into it as a sequence of shifting team patterns depending on task, state, and context. And common team patterns could include synchronous joint work, synchronous asymmetric work, or mixed models. What's important is to design involve transitions and handoffs between those patterns. And again, another important point is that a highly autonomous pattern is actually a pattern where a human backup role is needed and required to continue monitoring and be ready to intervene. Then we go to one point from coordination and communication, and which is multimodal coordination. And essentially, yes, the problem changes from autonomous control to support for effective coordination under changing conditions, updating shared mental model, balancing goals, ensuring observability. And what's interesting is that, which means that we don't only need feed now and feedback, but also feed forward, which is something that we saw missing in the construction studies quite a lot, which is, yeah, connects to compensatory control and anticipatory control. And one point from worker well-being is autonomy and job crafting. And essentially, yeah, from fragmented ownership to enabling agency, feedback, and flexibility. And structurally or technologically, it looks like open-ended automation that allows roles and tasks to be shaped dynamically. It's an active process, which means that people have a certain level of control over the robotic systems. Authority responsibility should be very clear to avoid double binds, which is when workers are accountable but unable to exercise real autonomy, which happens quite a lot with robotics. And ownership and purpose as explicit design goals embedded in the system. Something important also for us researchers to remember is like avoiding psychologist fallacy, which is the mistake of confusing the designer's or observer's vision of work with the lived experience of those who actually perform it. And to close this presentation, I wanted to put some questions to potentially inspire a discussion. And I can come back to it with, and this is a bonus slide, because I never know if I go too fast or too slow. And these are also two perspectives from meaningful work studies. That one is realization, which is based on self-development theory, and another is justification. And I think I will leave with that.
Okay. Thank you, Angelina. Thank you for your presentation.